Done. Okay, well, welcome everyone. My name is Greg Peterson. I'm the Director of NICS at the University of Tennessee, National Institute for Computational Sciences, and I'm also a professor in electrical engineering and computer science. And so I'm going to talk to you all today about supercomputing and why it's important for you. Okay, just to start off, so as I said, I'm the Director of NICS. So the National Institute for Computational Sciences is one of the NSF's supercomputing centers. So it's here at the University of Tennessee. We had been operating Kraken, which was a 1.2 petaflop Cray XT5 that we just retired this year. It had been the most productive supercomputer in the NSF's stable of machines. Currently, we're running machines called Darter, Nautilus, and Beacon for the community to use. And we're also very much involved with XSEDE, and I'll mention a little bit about what that all means. And this is a picture of our building where the folks are located. So it's a UT building we have out at Oak Ridge National Lab. Okay, so since the title of NICS says computational science, and we're talking all about supercomputing, I thought I would just step back and just talk for a moment about what is computational science and engineering. So it's kind of emerged over the last few decades and is now considered to be the third pillar of science. So you, of course, go back for millennia, we can talk about folks who've been using experiments and empirical methods in order to try to understand systems, and then using analysis and theory in order to try to figure out what's actually going on, be able to predict and everything like that. But in the last few decades, with computing becoming very powerful, the use of simulation has become a pretty popular way for us to try to understand systems. And so now we can simulate systems and to be able to explore behaviors and understand them. And so there's a lot of examples of simulation. For example, with our NICS resources, we have literally thousands of users. So there's huge numbers of codes. But some of the examples include things like being able to do weather and climate kinds of simulations. So it can be extremely challenging. With chemistry, folks will want to go in and perhaps design reactants, try to do rational design of drugs for biology. So for example, looking at various kinds of proteins and how they might fold, and looking at what might be good ways to perhaps bind to a particular location to promote or repress behaviors for biology, so you can build drugs from a more rational way as opposed to just experimenting in the lab. For example, physics, there's lots of things such as astrophysics kinds of areas, as well as in engineering, things like nanomaterials, designing reactors, designing airplanes, spacecraft, etc. So it's a huge number of different kinds of areas that have sprung up, and using simulation is a very powerful way for us to be able to explore systems in order to be a lot more efficient with our science. So at the University of Tennessee, we've got something called the IGMCS. It's the Interdisciplinary Graduate Minor in Computational Science. And that's basically kind of the way that we do our curricular work related to computational science and engineering. And there's three legs for this. So there's the computer science, so being able to write code, to be able to build our applications, to be able to, say, simulate things. There's mathematics, which is a basis of all of this work as well. And then finally, there's the various domain sciences in engineering. So for example, physics or biology or economics or civil engineering would be the domain science. And so it's a combination of all three of these kinds of areas as well. And so from a curricular perspective, we're doing a lot of work related to computational science and engineering with this. Okay, so because of this, we've had a fundamental shift in the way that we do the work. So as I mentioned, this has been called the third pillar of science. This is a big change in the way we can do it. So for example, using simulation, we can explore the past, or we can explore the future in ways that you wouldn't be able to do with any kind of empirical measurements. We can also look at speculative kinds of systems or remote or dangerous kinds of locales. So it's kind of hard for us to go in and measure things in the inside of the sun, or something on the other side of a galaxy, or things inside of a nuclear power plant, whereas simulation makes it a whole lot easier to go in and do that. We're able to do larger, more refined models. So if we did an analytic kind of a model, a lot of times it becomes intractable to be able to do interesting things. So, for example, Schrödinger's equations are really hard to solve in any kind of interesting scenario, and so lots of compute time is spent to try to do analysis, to try to approximate the answers we can also add in additional physics. So not only can we look at the physics that we've been looking at, but over time we've been able to add more and more factors and be able to look at not just primary but secondary and tertiary kinds of factors as well, and how they might interact with one another, particularly with coupled kinds of simulations. So one looks at how one might want to say explore what the climate might be 1,000 years from now, and looking at the impact of, say, carbon being released into the atmosphere. There are a lot of different kinds of simulations for how weather patterns and how climate kinds of patterns are going to evolve. And that can include oceans, that can include chemistry in the atmosphere, et cetera. And so coupling these kinds of things together, all of these things taken in combination, it's been a fundamental shift in the way that we do a lot of our work. And so this is tremendously powerful for us. And many of us have been used to the idea about doing this kind of thing just on our own kinds of systems in our lab. But if you look at a machine like Kraken, which was our big machine, it had 110,000 processing cores roughly. So there's about, say, 18,000 or so sockets in it. So if you look at a machine, it's about that same kind of size, something on that order. So a pretty big system. One day of computation on a machine like that is the equivalent of about 60 years on a desktop. So the amount of work that one can get done with these kinds of large computers is really dramatic. And oh, by the way, a machine like Kraken, it's not just that I can do more work with a small problem. There are qualitatively impossible things you could not possibly fit onto a desktop machine. So I can just qualitatively do different kinds of science. I can look into different kinds of issues. So one of the things that just happened about a year ago, the Nobel Prize in Chemistry was awarded. And so there are 3 professors from Harvard, Stanford, and Southern Cal who were awarded the chemistry Nobel Prize for their work related to computational science and supercomputing. So that kind of is a way to kind of put the stake in the ground and say, yes, this has really changed the way that we do science, and it's the impact is pretty obvious. At the same time, while we talk about all this kind of stuff with, say, simulation-oriented kinds of computing, there's also this idea of computational and data science and engineering. So the emergence of data as a first-class citizen has happened in the last few years. So folks have been gathering data for quite a long time, but going in and doing the analysis on this data and being able to discover new things is really kind of exciting thing. So some have been starting to call this the 4th pillar of science. And so just like the idea of using computation and simulation as a way to try to understand systems is really important, we have so much data that we can be gathering around in our world that we can be collecting, and being able to do various kinds of analytics and visualization on the results of experimental kinds of things from analysis or even from computational simulation. All those kinds of results, being able to sift through all of that kind of result presents really interesting new opportunities. And so this is a cartoon of a data life cycle. And so for folks who are data scientists, the idea isn't just a matter of just looking at the data and thinking about it. You have to plan on it, collect it, and go through this whole cycle, including bringing it in, keeping it, preserving it, being able to discover the data. That's a big challenge. Then integrating it, and then finally, what a lot of folks think of for data science is just this piece here. We're actually doing the number crunching on it. But the reality is there's all of this that actually has to go on with it in order to be able to find the data and manage it and deal with it and all the rest. And so this presents interesting new opportunities for us as well. So when we have large simulations, let's say somebody wants to simulate, say, weather across the country, being able to go in and try to identify where there are interesting events out of maybe terabytes of data is an interesting problem that comes up. But by the same token, if you look at all the Twitter feeds that are out there, if you're looking for interesting trends in the social media, the data science folks are really excited about a lot of that stuff. So actually, what we do at UT is, should say, CDSE, so Computational Data Science and Engineering. We have both computer and information science. So the information science folks have been thinking a lot about how do you take the data and deal with it over long times. In addition to math, statistics has grown up as being a really important field as well. So for a lot of the data science kinds of things, statistical analysis is what's going on, in addition to the traditional kinds of domain science and engineering things that we've talked about in the past. I guess one other thing I will actually point out with this, one of the things that's an emerging behavior for computer users who are interested in data science in particular, is this is moving beyond the traditional sciences. It's not just physics. You're starting to see humanities, social sciences, and other kinds of groups starting to use that. And I'll stitch in some of that as I talk later on. Okay, so having said all that stuff about what's computational science and kind of real high-level introduction about all that stuff, I want to mention just a little bit about coming back to supercomputers and why you should care. Well, supercomputers are the engines. So at the highest end, the supercomputers are what allows us to do this computational data science and engineering. So there are systems like inside your iPhone or your Android. You've got processors in there, laptops, desktop servers, etc. There are billions of processors that are in the world. There's lots of them that are out there that can do a lot of really, really interesting kinds of things. But what makes supercomputers unique is that we're able to tackle the largest kinds of problems, the most complex kinds of problems, if you will, the grand challenge kinds of problems. That's what supercomputers were meant for, and that's when we deploy a supercomputer, that's the kind of target that we're looking at. So this is just a cartoon. It's kind of looking towards the future of supercomputing, particularly for exascale. So we are currently sort of in the petascale, where a petascale, a petaflop is a quadrillion. So 1 with 15 zeros on it. That's a petaflop would be that number of scientific calculations, floating point calculations per second. And around the end of the decade, early next, we're going to hit the exascale, an exaflop, which will be 10 to the 18th of those operations per second. So the idea is we're moving to the point of this exascale class, and we're currently at petascale class. And there's some smaller systems, and you get down to campus levels, and then maybe what might be in your labs or on your desk in your office. And so there's a pyramid, and there's lots and lots of these. There's a smaller number at each one of our campuses. There might be some regional kinds of systems, and then there's just a small number of true national leadership kinds of facilities for supercomputing. And these are about doing the biggest, most challenging kinds of problems. And you as researchers could be starting from these kinds of systems and moving all the way up to these to be able to handle and take on much broader, more challenging kinds of problems. It's a lot of really interesting things that go on with that. And of course, there are challenges with being able to take your code, your problems, and scaling it out to being able to use these biggest systems. So not everyone will use supercomputing necessarily. You may not climb all the way to the top of that, but the kind of skill set to go from one workstation, or say using one processor thread, and potentially talking about being able to use millions of threads of execution, that's the kind of thing that we're talking about here. And supercomputers are the engines that allow us to be able to do these gigantic problems. So I just want to kind of walk through just a few. So I mentioned Kraken a few times already. So Kraken, this is a picture of Kraken. So Kraken was 100 cabinets. Each cabinet is basically, if you think about a refrigerator size kind of thing for computing, there's about there are 100 of them, and inside of it we had a little over 110,000 processor cores. So it's a pretty big system. And over its lifetime, Kraken delivered a little over 4 billion processor hours to the community, with 147 terabytes of memory and all these details around it. So it's a really big system, and we were able to do a lot of really interesting science with this large system. In addition to Kraken, now we're running a much smaller system called Darter. Its peak performance is about 20–25% of Kraken's, but instead of 100 cabinets, it's 4. So it's a much more compact kind of a system, where it's using Intel's Sandy Ridge processors. So this is a newer system that we just deployed about a year and a half ago. And it's got on the order of 12,000 cores, 1,500 sockets. When I say socket, that's a chip, if you will, with a bunch of cores inside of it. And so it's about a quarter, or a little under a quarter of a petaflop in its peak performance. So Darter is available, and it's a Cray Cascade. It's an XSEDE system that we have. And so that's for being able to do large number crunching. Now, Nautilus is a machine from SGI, and it's an ultraviolet, a UV1000 processor. It's got about 1,000 cores. So it's a much smaller number of processor cores than, say, Kraken. But what's interesting about it is it's got a total memory of 4 terabytes. So it's a shared memory system, and so it's all about being able to do visualizations and data analytics on large problem sizes. So whereas on Kraken, you've got on the order of a couple gig of memory per core to be able to use. Each node has about 16 gig. This system has 4 terabytes. So you can bring in, you can ingest a much larger problem to be able to do your analysis. So you wouldn't use this to do a giant kinds of a simulation like I was talking about, say climate simulation or something like that, or say some huge astrophysics kind of simulation. But then when you've got the results coming back and you're trying to sift through that and trying to find patterns and do some analysis and correlations on large data sets that come out of it, that's what this system is all about. And so it's a really nice system for being able to do that kind of thing. So there's different kinds of supercomputing platforms that are designed for different problems. And so we also have this Nautilus system available for being able to do that. One of the other interesting systems that we have is something called Beacon. And so it's basically targeting power-efficient, high-performance computing. And it's using Intel Xeon. So the prior machine was not prior, two before the Darter system has Sandy Bridge processors, Xeon Sandy Bridge. So does Beacon. So they're also Sandy Bridge. But in addition, it's got these new processors that Intel has called Xeon Phi, or what is also known as MIC, Mini Integrated Core. And so they're accelerator or co-processors that are added on top of it. And so using this kind of a system, we were able to get just a hair under 2.5 gigaflops per watt, which was the world record as of November 2012. So it was number 1 on the Green 500 list a couple of years ago, with about just a little north of 70% efficiency. So it's a pretty interesting system. So in addition to having these mics and being instrumented to be able to explore power, efficiency, energy, and all that kind of thing, it's got a lot of memory per node, and SSD per node, and it's got 4 of these Xeon Phis per node. So that's kind of an unusual configuration as well. So this is a system which is all about trying to explore these next generation kinds of processor architectures that are becoming available to the community. So we've got a diversity of different kinds of machines that are out there. I guess one last thing I would say is Beacon looks more like commodity kinds of clusters. So you've got Darter, which has got a Cray custom interconnect, and so it's all about high-end supercomputing, number crunching. You've got Nautilus, which is a shared memory system for being able to do data analytics. And this looks a lot more like a conventional cluster, but with some extra instrumentation and using some of these new processor architectures. In addition, at NICS, we're partners with Georgia Tech. So Georgia Tech won a machine called Keeneland a few years back. And it's a heterogeneous machine, and instead of using these mic accelerators I talked about in the last slide, it's using GPUs. So GPUs are graphical processor units, which turn out, if you're not rendering images and doing number crunching for that, you can also use them for scientific computing. And so this is a system that's built out with a whole bunch of GPUs. And so it's got a peak performance, which is on the order of 650 teraflops. So about 2/3 of a petaflop inside this particular system. So NICS is partnered with Georgia Tech. So we operate it for Georgia Tech. So we've got a diversity of different kinds of systems that we have available for folks to go in and use. So one of the other interesting things that we've been doing at NICS as well is we had a project called BLAST that's just kind of ramping down right now. So we basically just upgraded the campus network to 100 gig. So now you can get a lot faster transfers of data in and out. So over here on the left, this is just a cartoon showing on the national level a map for Internet 2. So Internet 2 is a large organization that does networking across the country. And all the red dots are where they have what they call AL2Ss, so Advanced Layer 2 sites. So basically, we tap into the AL2S, which is down in Atlanta, and so we can get 100 gig networking with that. And so this is just a cartoon kind of showing our network. So in addition to having that, Internet 2 supports SDN, which is software-defined networking or open flow. So we're able to do some experimentation and start looking into how can we start scheduling or setting aside bandwidth and providing quality of service for data transfers. So we start talking about these large data things. If we want to be able to go between sites, this is a big deal for us. And so a lot of the supercomputing centers now have 100 gig support. I'd be remiss if I didn't at least make some mention about what's going on as well out at Oak Ridge. So, the machine room where Kraken was located is also the same machine room where Titan is located. So Titan is about twice as big as Kraken as far as numbers of cabinets go, but whereas Kraken was 1.2 petaflop. Titan has a peak performance of about 27 petaflops. So it's the fastest machine in the US, and for a while it was the fastest in the world. So it's a Cray XK7. Any day now, the Oak Ridge folks are going to make the announcement for the machine that's going to replace Titan in a few years. So keep your eyes open and your ears open to hear about all that. But one of the things I wanted to point out is Oak Ridge is also, if you look at their computing directorate, experiment, theory, simulation, and data, the same thing I was just talking to you about a few slides ago. Well, Oak Ridge is also structured in similar ways to be able to explore these kinds of things with their organization and what they're all doing. And so there's a lot of interesting work there as well. So in addition to all the machines I just talked about, so folks at UT, or actually anywhere in the country, can be trying to get time on the machines at UT. There's also mechanisms for you to get time on machines like Titan as well. So the cyber infrastructure with supercomputing includes a lot. So I get
our next session on Thursday is going to be about how to get an account.
Yes.
On our resources, XSEDE resources, and Oak Ridge resources.
Yes. So there, if you looked at the URL, there's a whole bunch of talks that are coming up. So I'm kind of giving hints towards some of these things. I'm not going to give all the details by any stretch, just because of time. But yeah, next talks should start to get you some of the information about what kind of resources are out there, because there's a lot more than just at Tennessee. There's other supercomputing centers. There's ways to get your hands on any number of these resources. But one of the questions is, so why do we have all this stuff? So I kind of said, yeah, computational science is important and interesting and all that kind of stuff. Supercomputing is good and all that kind of thing. What I wanted to do, just for a few minutes, is I wanted to just kind of give you a sense of some of the projects that are out there. So with Kraken having 100,000 plus cores, 112,000 and change cores, it's a big system. We had literally thousands of people using it. And Nautilus was being used by an awful lot of folks in conjunction with that. Now we've got Dart and Titan, et cetera. There are a lot of people that are beating on these things. So I just want to give a sense of some of the projects that are out there. So here's a project which is all about doing some molecular dynamics kinds of simulation. And so basically, in combination, so basically some of the life sciences folks at UT in conjunction with some Oak Ridge folks did some of this work here. And essentially, what the principal investigator is saying is we were able to provide some unique capabilities with the supercomputing, as well as with some of the accelerator imaging kinds of things that are out at Oak Ridge with the spallation neutron source. So Bronson Messer has done some interesting works with looking at supernova explosions. And so being able to go in and have a lot more detailed kinds of simulations. So the way that a lot of the astrophysicists have looked at, say, the way supernovas have worked over the years, they've had to make a lot of assumptions based on what they could actually do from an analytics perspective and then eventually from a simulation perspective. And so lots of assumptions about symmetries and various dimensions and things like that. And over time, as the machines have gotten a lot more powerful, they've been able to relax some of those assumptions and go in and confirm or discover that, oh, those assumptions were actually wrong. And so there's a lot of really interesting things. So being able to go into multi-dimensional models with a lot more detail and a lot more physics is really, really interesting for them. Robert Harrison and Deborah Pinchoff did some work with chemistry kinds of applications as well. So one of the things they're looking at is lanthanides, and so they're just basically trying to figure out for these kinds of chemicals, they wanted to do some ab initio calculations using a code called NWChem in order to better understand some of these kinds of things and basically figure out what can they do to design and extract these kinds of chemicals. So basically improving some of the chemical processes. I just skipped one. Oh, no, I didn't. Back to the theme of physics again. We want to simulate what happened with black holes in the early universe. So this is an example of something that's not tractable from an analytic perspective, and good luck with doing it measurements. So simulation gives us a unique capability to be able to understand what happened back then. And so there's codes like Gadget that are being used, et cetera, to be able to understand all this. And so these are folks out of Carnegie Mellon. Here's some interesting work from the folks from CAPS, so the Center for Analysis and Prediction of Storms. So in Oklahoma, there's a group called CAPS, and they want to go through and they want to be able to do what amounts to real-time simulations of storms. So Oklahoma, for those of you that may not know this, Oklahoma is kind of famous for the tornadoes and the really big storms they have, particularly in the summer. So there's a lot of really scary things that can happen with giant weather events out there. And so they want to go in and they want to be able to simulate a lot of this kind of thing. And so using a lot of these simulators, so for example, using Kraken and later on using Darter, they were able to do a series of simulations to be able to validate in real time whether their simulations were very accurate and tying it in with radar data. So that's what at the top. So they're actually trying to tie in real-time radar information with these kinds of simulations to be able to get a lot more accurate results. One of the things that's really kind of interesting that happened a year or two ago was they were able to get some results with the supercomputers at NICS and predict that a large tornado was going to hit just a little bit before it did. So they're actually able to get some node out, and that may have saved lives because it was a very large tornado. And kind of tied in with that, Amy McGovern is also working with those folks. And so this slide is talking about doing some of the analysis with all this kind of thing. So a lot of the work with machines like Nautilus to be able to go through and understand. So here's tornadic storms. So basically tornadoes. So they want to try to understand about what's going to happen with tornadoes because they're deadly a lot of times. So we use Kraken and Darter for that, and then Nautilus for a lot of the post-processing and data mining. So I just wanted to mention this to show that both pieces of those were pretty important for their workflows to be able to do their science. So coming out of NCAR, here's some, basically what this is all about is there's a bunch of planets that are out that we've seen. There's a bunch of objects that are off in the universe, and we're trying to basically understand, are these in kind of the sweet spot where they might be planets that could have life? And so this is basically just going through and doing a lot of number crunching to be able to go through and do that. And here out of Duke, we've got materials genomics. So the whole idea about material science and trying to explore new kinds of materials, there's a lot of very interesting work going on with regard to materials all the way down into quantum kinds of effects and trying to explore how we might be able to build kinds of materials. In this case, is looking at some insulators. Here's some more supernova kinds of things, and looking at how neutrinos were involved with that whole process. So some pretty interesting physics behind all this with this work. And so this is coming out of RIT, Rochester. So one of the things I'm also trying to point out is these are folks from all over the country that are using these resources. So a number of them were local, but there's folks from all over that are doing that. And I guess I should also point out that down here they're also pointing out a lot of the help from the staff. So a lot of the NICS staff, some of their job is to actually interact with various research groups, help them get their codes tuned so they can get good performance on these kinds of resources so that they can get their science done. Ultimately, that's really what we're trying to do, is we're trying to get the science, get the research done. So moving into more of a life science kind of oriented thing. So if I'm looking at DNA, one of the questions that we can start looking at, this is actually motivated by the idea of I want to be able to sequence things, and so eventually I want to be able to do this. So this is all about if I look at the DNA and how it starts to go into different kinds of pores or some interface like that, we'd like to be able to model that and understand that so we can try to do a better job of capturing this, and we can do some sequencing based on all that. So there's some interesting things that tie in with all of this work with life sciences. Continuing on, we can look at some kinds of nanostructures and basically trying to understand how these things kind of fit together and work together. And so this is more work that's kind of life science related using Kraken. It's out of Temple. So one of the interesting things that's been going on as well, so for folks that are trying to figure out how can we try to do renewable energy kinds of things. So I want to be able to take, whether it's trees or plants or whatever it might be, corn, I want to be able to extract that and turn it into something like ethanol or some other kind of biofuel. One of the challenges is how do I strip away the cellulose so I can get down inside the plants and get to the sugars and things like that I can turn into fuel. And so these guys are looking at how can we go in and basically engineer, say, bacteria or things like that. You can engineer to try to go in to try to strip away the cellulose. They're going through and they're trying to simulate the chemical processes about all that. So that's pretty interesting kinds of things. So in Tennessee, one of the things we're looking at is switchgrass. And so the big problem with switchgrass, it grows really fast, and it's really cheap and easy to go in and do. But if we can strip away the cellulose, now we can get all those sugars out and we can use them for fuel. And so that's a lot of what this is all about. Similarly, here's an example of proteins, and we want to be able to look at how protein and water are going to interact. And this is some implications for some of the drug design kinds of applications. So yet another kind of life sciences. So actually, I think I have one or two more. Here's some folks out of South Carolina in conjunction with Tennessee that have been looking at basically various kinds of carbon kinds of structures. And if I just bombard them with hydrogen, what happens with regard to the dynamics of that for some biochemistry applications. So more life sciences, material science kinds of things. And then finally, I think this is the last one I'm going to talk about. This one's a little bit different than all the other ones. So most all of those things, so we had a lot of traditional chemistry and physics kinds of things, and then life sciences has really grown in the last decade. It's really exploded onto the scene. This is computational finance. So there's some really interesting work that's been going on across the board with economics and other kinds of fields. So can we try to understand what's going on as far as, in this case, optimal contract design? So interesting kinds of research about how would one do things to make our financial system be a little more efficient, et cetera. So a lot of interesting results from that. And this is folks out of MIT. Okay, so once again, the idea isn't to try to cover every single thing that we end up doing. The point is to show that there's huge diversity. There's a ton of different things that are going on, and actually that diversity is exploding. It's more and more different communities are starting to get onto these kinds of machines. And the kinds of problems they're looking at, there are a lot of really interesting kinds of things in there. So you got, physical sciences and engineering have been kind of traditional users of supercomputing, but life sciences and now humanities and social sciences are coming on board. And particularly with respect to the data. So everybody has data. So we're used to the idea of physicists maybe using these kinds of computers, but the biologist folks, a lot of them, even if they're not doing simulations of things, they've got lots of data that's been coming in from their labs. And being able to sift through all that stuff and start doing correlations and trying to understand stuff, the knowledge discovery that comes from that data is really important. And in the humanities and the social sciences, that might be a key way for those fields to be transformed into being much more computing oriented. And so we've got some incredibly powerful tools that can help with doing that kind of research. And these are national resources that are available. They're available for your research. So as a student or as a faculty member, you have the opportunity to go out and try to start using some of these kinds of resources. Especially those of you who are local, it's really, the bar is not that high for you to be able to get time on these resources. You should be trying to do that sort of thing to see if it'll help you. Okay, just to kind of switch gear, I've been kind of focusing an awful lot on it from kind of a Tennessee perspective. So between NICS and OLC at Oak Ridge Leadership Class Facility, there's a lot of supercomputing kinds of capabilities locally. But there's also something called XSEDE that I thought I'd talk a little bit about. I'm a co-PI in XSEDE, and I'm the director of operations. So I've got some involvement with this whole thing. But basically what XSEDE boils down to is, if you look here, we have San Diego, Texas, Illinois, UT at NICS, and then Pittsburgh are the 5 major NSF supercomputing center sites. And XSEDE is essentially tying all these things together so that researchers from all over the country, or literally around the world, have one place to go to be able to get access to these resources, to get training for these resources, et cetera. So it's basically trying to integrate it into a single cyber infrastructure. And so that's kind of what XSEDE is all about. And so there's a bunch of different resources that are available. And so NICS is a service provider with Kraken, Darter, Nautilus, like I talked about. And we're also working with Georgia Tech for Keeneland. And there's other service providers all over the place. And so there's a lot of interesting machines that are out there. And so this is a pretty interesting kind of a way to be able to get to resources, not just here, but all over the country. So if you look at the NSF strategic plan, basically the NSF, it's the National Science Foundation. So they are all about trying to do science, and they recognize computing and data as key components of this whole endeavor. So if you will, the third and the fourth pillars of the way that we do science, the way that it's done now and into the future. And so they've done all kinds of studies, and so this is basically just some of the vision kinds of things that are all about that. And so XSEDE is largely about trying to build some of this cyber infrastructure. And so they defined something called CIF21. So basically, it's the cyber infrastructure framework for the 21st century. And so advanced computational infrastructure is a key component of being able to do this innovation and discovery. And it ties in with a lot of the other pieces that go with all of that. And so the idea for all this is how can we make it so that we've got the next generation folks trained up to be able to use these resources. We can make the resources available for you to be able to do your research so that none of you are going to be slowed down. So you can make the contributions and the discoveries that are going to drive our economy and our knowledge as we go forward. So basically, XSEDE, one of the things that are kind of distinguishing about it is basically we're providing this foundation for a national cyber infrastructure ecosystem. So we'd like it so that whatever campus you are, whatever state you are, you have the ability to get into these kinds of resources. And so we want to try to make it as simple as possible. And so there's campus kinds of things. We want to try to integrate with all the various campus resources, as well as tying together these national kinds of resources. And so there's a lot of really interesting things about all that. So there's a strategy behind all this that we're actually trying to pursue. So this is a cartoon which is basically showing major sites within XSEDE, and they're connected together with what we call XSEDE. So we basically have tied in with Internet 2 for this as well. And so the various sites have advanced layer 2 service connections. And so TAC in San Diego and CSA and NICS in Pittsburgh are all tied together using XSEDE. And so we have peering with high-speed networking between these various sites. So that's really interesting because let's say I want to use some of the resources in Texas or San Diego, but I also want to use the resources that we have at NICS. So I can move data back and forth between them, and I can do some of the number crunching on certain machines that are really good for that. Maybe I can move some data and I can do some other number crunching if I need it at other spots. Or if I've got some instrument at one part of the world and I have some of the data stored, I can use this networking to help me to bring that data into the number crunching that I need for my science. So continuing on a little bit more about XSEDE. So I mentioned operations. So I'm in charge of the operations, and that includes a lot of stuff. So the security related stuff, the networking kinds of things, data services, how do we keep track of accounts for your jobs and everything else. The help desk, so when you have a problem, you call in, you get help. That's all part of it, as well as software testing and deployment to make sure that everything works and then his quality and all that kind of stuff. But there's also user services. So one really nice thing is there's training. So you got one place to go for training. So if you're trying to figure out how to use the machines at different different kinds of machines at different supercomputing sites, there's one place to go for training, which is really nice. Same thing goes for allocations. If I want to have time on a variety of different supercomputers, I write a proposal one place, and I say I want them on these different machines. So that makes life a lot easier. So it reduces some of the friction for researchers being able to do all that kind of stuff. And there's user engagement to just help folks along. And then there's something called Extended Collaborative Support Services, which is essentially kind of the advanced user support. And there's things like gateways. So a gateway is essentially, I take some supercomputer code and I put a web interface in front of it, and now I can basically let folks just submit jobs, and they don't have to know anything about what's behind it. They don't have to know anything about supercomputing. You can just submit their job and let it kick back an answer. And so gateways are a really popular way to use some of these resources. There's a lot of that that's out there. And there's also a lot of community codes. So if you talk to a chemist, they might want to use, say, NWChem, or they want to use NAMD or something like that. There's a bunch of these common kinds of codes that are used. And so we also have been working to try to tune these codes to work really well on various machines so that everyone that's going to use these kinds of things will get the most efficient usage as possible on these resources. And then finally, EOT is education, outreach, and training. There's an awful lot of work that we're trying to engage with campuses all over the country to help with building up a community and a lot more folks involved. So that's important enough I thought I'd just mention. So I already said about training, really important. So I talked about GPUs, I talked about mics, there's these new kinds of processing devices that are out there, training how to use those kinds of things. But even if you're a brand new user to any of these machines, you need training. Well, you don't have to have one different set of training for each one of the sites. We've got integrated training between all of them. And of course, you're doing this right now, for those of you who are webcast on this. There's a lot of educational kinds of things that are going on, curricular development. We've got courses going on right now where sites are doing the course and then campuses all over the country are participating. UT is actually participating with courses right now with that. And there are all kinds of interesting outreach ways so folks can get involved. One of the interesting things that I'll mention in just a second is called Campus Champions. So I'm going to kind of table that for just a second. But one of the things that I mentioned kind of in passing is this idea of campus bridging. So there are hundreds, thousands of campuses across the country where people might be interested in interfacing in with these resources. And so there's a really important effort to try to figure out how can we tie in with all of that. So this picture right here is showing campus champion institutions. So basically, if you wanted to have somebody at your campus, so for those of you who are watching on the webcast, if you don't know about XSEDE and you want to figure out how can I get my users connected in, these are all places where there are campus champions. So, so UT, we're on the map, we have a campus champion, and so their job is to help the faculty and the students on a particular campus to understand how to integrate back in. And they actually can get their own allocations. So if you're trying to figure out how do I use the machine, they can help you kind of get your feet wet, try it out just a little bit. And that's all over the place. So you look, I mean, they're all over the country. Maine is the only state where we don't have a campus champion yet. This is about a month and a half old data, so it's from mid-September. And at the time, it was 174 institutions. I'm fairly certain this number is wrong. It's bigger now because we keep adding them. Seems like every day or two there's another school that gets added in. But this is a really interesting program as well. Okay, so just kind of step back a little bit. We're talking about national cyber infrastructure, and supercomputing is a key component of all that. So there's all the number crunching and the data management, the data movement, all that kind of stuff that goes with that. And so there's XSEDE and the NSF kind of supercomputing centers, and these are the main five. So NICS is here at Tennessee, and so I'm from there. As well as there's a whole bunch of smaller places that are out there as well. So campuses all over the country have additional resources. In addition, there's the Department of Energy, and there's leadership class facilities. So OLCF is the Oak Ridge Leadership Class Facility. So Titan is the big machine, the flagship, if you will, of OLCF. And so the Department of Energy also funds a lot of research. And so there's the capability for folks to get time on these kinds of machines. So Argonne's is the ALCF. And so there's a big machine there. And then NERSC is another site that's available for folks. So the DOE as well as the NSF provide a lot of computing power. And for those of you who are in Tennessee, OLCF and NICS are both located here. So there's a pretty amazing amount of computational capability located right here in East Tennessee. That's one thing I wanted to just kind of mention. And as well, those of you who are in Tennessee, and more specifically even at UTK, there are a lot of ways that you can get involved. So NICS has the ability to provide directors discretionary hours. So we have procedures for folks to get initial some hours to be able to start doing some research. So if you got an idea, you can get something, and it's not the next, not the next day, but pretty quickly you get feedback and you can get on your machine in not too long to try things. We're also tied in with both graduate and undergraduate education, particularly at UTK. So I mentioned this IGMCS, and there is this seminar series right now. We've had ties in with various kinds of classes. And we've got lots of GRAs, so graduate research assistants that are available in internships. And we have an REU site. So anyone around the country that's interested who's an undergrad, REU is a research experiences for undergraduates. We have a site that's focused on computational science called CSURE at NICS. So we'd be thrilled to have folks from all over the country come participate. We also work with educators, so K through 12 in particular in this case, along with a lot of different kind of training things. So this whole seminary series, and there's a lot of other things that we're doing to help folks to learn. And then this last thing is there are things related to cyber infrastructure we've been doing with campuses across the state. So it's not just at Knoxville. So I wanted to conclude by just noting that now is a really exciting time in computational and data science. There's a lot of really amazing resources that are available to you. The networking is pretty impressive. There's huge amounts of data that are available to you. So there's a lot of really interesting things to look at. And these new architectures that have been coming online show great promise for you. So I would highly encourage you. So In particular, if you're interested in interacting with NICS and with Oak Ridge, there are opportunities for faculty and students at UTK or at other campuses to engage with us, and we would welcome your participation. So I really want to encourage everybody that has any interest in it at all in this to go ahead and explore it, because it's a great opportunity. And like I said, we have some world-class facilities that are here. And so with that, I will stop and I will ask if there are any questions. Just a few minutes for Q&A.